Hey, how's it going? This time we're going to look at a simple stress problem. All right, so here's the problem description. We have some kind of rod or bar with some loads acting on it somehow. This is a bit of an abstract kind of a problem that you see in textbooks, but it's an introductory problem for solving stress or doing stress analysis. So let's go with it. All right, so we're asked to determine the magnitude and location of the maximum average normal stress in the loaded rod, and we have information about the cross section, that it's a circular cross section with a diameter of 10 millimeters, and we need to also, because we've got forces going in all sorts of directions here, we need to work out whether each section is in tension or compression. So we want to know what the maximum stress is in either tension or compression in this loaded rod. So solution: when we calculate stress, we in general take a cut through the section of the component somewhere. Now, you could possibly do this problem without going through this process, but it's a good idea to get into the habit of doing this, because you'll need to be doing this for later problems where we're finding stress components from bending and torsion and shear and so on. So even though you can probably bypass these steps and do it kind of in your head, best not to at this stage. Just learn to go through the formal process properly. Okay, so we're going to cut through each section, look at the internal actions and determine what they are using the equation of equilibrium. So in this case, they're all uniaxial, so we only need some of the forces in the horizontal direction. So starting at the right-hand end, we could start at the left-hand end if we knew what the reaction force was, and I'll do that at the end, but we'll start at the right-hand end where we've got a known load, take a cut through section AB, draw the free body diagram. So here's what we have left. So we've imagined that we've taken a cut through there somewhere like that. And then internally, we have some internal actions that are acting on this cut section. Right, so this load that we have out on the end here is transmitted through the body of the structural component, and the internal action that we have here is what this left-hand side of the component does to the right-hand side. Now you can see here that I've put this acting to the left when it's quite obvious just by looking at the problem that it's actually going to be to the right for equilibrium. So why have I drawn it to the left? I do this because we assume, or we make the assumption, that the internal action is positive or in tension, and then if we get a negative answer, that tells us that it's in compression. Okay, so we draw the arrow acting away from the section of interest, so that's indicating tension. If we get a negative answer, that shows us in compression. Right. As I said, you could have drawn the arrow acting into the surface and said that because the arrow acts into the surface, I know it's in compression. Either way is okay, but just in this example, I've chosen to show the positive internal action, and then if I get negative, it tells me it's in compression. All right, so pretty obvious that NAB here, my internal axial force, is going to be equal to minus 10 from sum of the forces equals 0, so it's in compression. So we now just continue the same process moving along. So the next section to look at is section BC, and then draw our free body diagram. Now we need to draw everything to the right of the section that we're looking at. So a mistake that students often make is to draw the free body diagram without that bit. Okay, don't do that. You need the whole of the section to the right. All right, so putting on all of the external loads that act to the right of the section, we also now need to include the 6 kilonewton force. And now we need to put on our internal action. So again, I show that as a positive internal normal force acting away from the surface. If I get negative, then it'll be compression, and I do get negative using some of the forces in the horizontal direction. 10 minus 6, or 6 minus 10 if you like, gives us minus 4. So that's in compression, so that's our internal force, internal normal force through section BC. So continuing the process, take a cut through section CD, draw everything to the right of the cut. So we now need to include this 2 kilonewton force, put on our internal action, label it NCD. Sum of the forces in the horizontal direction equals 0, so we get NCD is minus 6 kilonewtons, so again in compression. One more, take a cut through section DF and internal action, internal normal force, NDF. Sum of the forces equals 0, we get NDF equals minus 1 kilonewton, so that's in compression. Right, so all of the sections are in compression for this particular problem, so we don't have to worry about finding the maximum tensile stress. Our maximum internal normal force was in section AB with an internal force of minus 10 kilonewtons. So to work out our normal stress, our equation for normal stress, or the average normal stress, is the internal force over the area. Now the area is equal to pi d squared on 4, or pi r squared if you like. So the maximum normal stress, the normal internal force over the area, working in newtons and millimeters and megapascals, so 10 by 10 to the 3 over pi d squared on 4 gives me 127 megapascals, negative, so it's in compression. And as I mentioned, none of the sections of the bar are in tension, so don't need to worry about that. So as I said before, we could have also worked from the left-hand side to the right if we knew what the reaction at the built-in end was. So if we draw a free body diagram of the entire bar, we can work out what that reaction force at the end will be. From sum of the forces in the horizontal direction equals 0. So RF will be equal to 1 kilonewton. So if we now take a section through FD and look at the left-hand side, so we've now taken the cut through there, but we're now looking at the left-hand side of the cut. So we have our internal action, NFD, positive acting out of the face. So we have RF onto the left acting inwards, so sum of the forces horizontally equals 0 shows us that NFD, or NDF if you like, doesn't do the same thing, equals minus 1 kilonewton, which is what we got before. And if you continued from working along, you should get the same values that we got previously. All right, so that's the end of the problem. Pretty simple one, but hopefully it got you started with the process for being able to calculate stresses due to the internal actions, which are developed because of the external loading and the reactions on the structural component. That's it for now. See you next time.